This is Bob McFedrich with Beckwith Electric, and I'd like to thank you for downloading our training session on reverse power for the M-6200A. So the M-6200A is the latest of our single-phase regulator control products, starting with the original 2001 and now up to the 2001D. But the 6200A was engineered specifically and only for single-phase regulators. So unlike the 2001 line, the 6200A should not be used for load tap changer controls, LTCs, as we don't have adapter kits for each of the different LTCs. And also it does not have a second CT that would be required for paralleling of transformers. So the M-6200A should be used for single-phase regulators only, while the 2001 series platform should still be used for load tap changing transformers. But on to reverse power, which is the subject of this particular session. So, in the software for the M6200, which would be the S6200 software, if we go to the set point screen, we can see that we have a reverse power option down here. And depending on which operation mode we select will determine what of any of the settings down below that we can set. And the first setting we can select is block. What block says is in reverse power flow, do not regulate. So if power is flowing forward, allow both raises and lowers, but if we detect reverse power, we will block and not allow local, automatic, or remote controlled raises and lowers. It would still allow, if you put it in local via the panel local manual, you would still be able to issue a raise or lower there because you're basically taking the control out of play at that point in time. But it will block both local automatic and remote controls. So this mode should be selected when you do not anticipate reverse power as a possibility. For instance, if we have a radial circuit, we have no generation downstream currently, there should be no reason we should see reverse power flow. So if for some reason we were seeing reverse power flow, we may want to block. Now, before we go any further, it probably would be good to define what exactly is reverse power. Well, that is set by another setting on the same screen up here, the power direction bias mode. So our default setting is none. And when you set it to none, what that says is the control must see current flowing in the reverse direction for 5 continuous seconds, and that current must exceed 4 milliamps secondary for those 5 seconds in the reverse direction before the control will change from forward to reverse. Once in reverse, again, if we have it the bias setting set to none, once in reverse we need to have 4 continuous milliamps of current for 5 seconds in the forward direction to bring it back to forward. So basically, if we set that setting to none, what we are saying is we need to have at least 4 milliamps of current for 5 continuous seconds flowing in the opposite direction to switch from one direction to another. Now, another thing to remember is that 4 milliamps of current must be 4 milliamps of real current only, because the reverse power is looking at real power only, not reactive power. So we're not looking at forward or reverse megavars or MVA, we're looking forward or reverse megawatts. So when we're talking the current thresholds here, we're talking the real portion of the current. You may see on your screen on a control where you have 4 or 5 milliamps and it's not changing direction, and you may be curious as to why, and it may be because the majority of that current is reactive, and we do not want capacitor banks falsely triggering the operation. So for instance, we may have a circuit that's really in forward power mode with very little load on it, but when a downstream capacitor bank closes and all that capacitive current comes on the circuit, that we don't want that to drive us into reverse power. So we are looking at the real portion of the current only. So with that setting, none means 4 milliamps in reverse for 5 seconds to go to reverse, and then 4 milliamps for 5 seconds from reverse back to forward to come back to forward. If we were to set that setting to forward, what that would do is the control would still require 4 milliamps for 5 continuous seconds to go from forward to reverse, but no current or any positive or forward flowing current will bring it back to forward. It still needs to be there for 5 seconds, but instead of needing at least 4 milliamps, no current at all or any forward current for 5 continuous seconds would bring us to forward. And reverse works exactly the opposite, where we would need at least 5 seconds to go forward with 4 milliamps, but to come back to reverse, no current or any reverse current would automatically, after 5 seconds, bring us back to reverse. And why you would set, so typically most applications we would recommend set to none. Why we would set it to one of these other two would be a situation we're going to look at in the next slide. So in this case, we have substations with LTCs. They each have line regulators, and we have a normal open point. But right beside this normal open point, we have a set of line regulators. And normally with that point open, the power is flowing this way, so we're in a forward direction, but we have very little load. The only load that may be on that regulator may be the exciting current of the regulator itself. So we may not have at least 4 milliamps forward. We may only have 0 or 1 milliamps normally. So then when we have a fault and we sectionalize, and we're going to open up this breaker and close this breaker, we close in this tie point, this regulator will go reverse power, and it'll have load on it now. All these customers which were on this regulator are now going to be on the load side of this regulator. So now we have more than 4 milliamps of current in the reverse direction, so we will correctly go into reverse power. But when we're restoring and we close this breaker back and then open the switch up again, we're back to having no current in the forward direction, and therefore if we were to use our normal setting of none, this regulator would be stuck in the reverse condition even though it was now in forward power mode again. And if this voltage were to get out of band, since it's in the reverse power mode, even though it's forward, it will have a runaway condition, and we can have extremely high or extremely low voltages on that little portion of circuit. So this is a case where we would go ahead and set our bias one direction or the other. So anytime we anticipate that in one of the two states, either forward or reverse, we're going to see less than 4 milliamps of current on the regulator, then we would need to address that with this particular setting. Now, our next possible setting for reverse power, now that we understand what reverse power is what we call regulate in forward or ignore mode. In this case, what we're saying is we don't care whether the power is going in the forward or the reverse direction. We are always going to apply our forward settings regardless. So you can see that if I select regulate to forward, everything is grayed out, so I'm not going to use any reverse power settings. I'm going to continue to use the forward power settings, but unlike the block mode, which was the screen would look similar, in this case we're not going to block. We're going to continue to regulate like we normally would, regardless of the power direction. And this typical application would be that if you had possibly some downline distributed generation that may be able to pump enough into the system to backfeed the regulator, and you're not using line drop compensation. So if we're not using any line drop compensation, we've got 0 for R and X, and we have downline distributed generation, then in that case we could probably set it to ignore, because we don't care what direction the power is flowing. We're still regulating this piece of the circuit. So in this scenario, this is still the load side of the regulator, even in reverse power, both in forward power and reverse power. The load side of the regulator is still the load side of the regulator, and we're still regulating the same piece of circuit. The only difference is the load is shifting the direction. That would be important if we were using RX, and we're going to see that in a future slide. But if we're not using any RX, then we could select ignore for this particular mode. So, in summary for ignore, the PT is still on the load side of the regulator. And that's the first question you always have to ask yourself in a reverse power mode is the source side of the regulator still the source side and the load side still the load side? And in this case, the answer is yes. We're still regulating the same piece of circuit, and if we don't have any line drop compensation, then we're fine to go with this particular mode. So looking at block again, block will not cause an operation. So it's the same exact, no settings are going to be applied in reverse mode, and that's because if we do see reverse power, we are going to block and remain blocked both raise and lower until the power comes back in the forward direction. So now distributed generation. If I do have distributed generation downstream and I want to use RX, then I really need to select DG mode, because when I select DG mode, you can see that it's still going to use the forward settings for band center, bandwidth, and time delay, but now it's going to allow you to have a different set of settings for R and X in reverse power versus forward power. And the reason that is done is, let's say I had a positive 4 up here for the R. If I had a positive 4 for the R, what that says is that full load current going in the forward direction, I'm going to add 4 volts to the band center, because I'm anticipating 4 volts of drop across this circuit, and if I want to keep it at 120 down here, and I know there's going to be a 4 volt drop at full load, then I need to be at 124 at the regulator control. What's not necessarily known is that in reverse power, if I leave it at positive 4, it'll do the exact opposite. At full load in reverse direction, it'll actually lower the voltage here by 4 volts. And so therefore, we can risk having under voltages at the end of the line. So with that in mind, we can do one of two things if we select DG. Number one, we can have our plus 4 in the forward and just have no compensation in the reverse. Or if we still want to cover that 4 volt drop, since this is still the device regulating, we would actually put a minus 4 in the reverse direction. And if we had a minus 4 here in the reverse direction, that would cause it to raise 4 volts here to keep that end of line circuit voltage up. So the reason for DG mode is if we're going to see reverse power due to distributed generation only, and we're using R, we know that we need to either not use it in the reverse mode or we need to flip the sign on it, because if we do neither and we leave it in place, instead of raising the voltage as the load goes up, it's actually going to cause the regulator to want to lower the voltage as the load goes up. So that's what our DG mode would look like. So for power flow in reverse, a positive R will raise the voltage in forward direction but lower the voltage in reverse direction. And we don't want to have the voltage lowered here as this current is going across this line, because it's still creating a voltage drop. This DG is not regulating the voltage. It's a constant voltage and it's a load. You look at a DG as what I would think is a negative load. Your normal load is not trying to regulate the voltage. It's just sucking current. This is doing the opposite. It's not attempting to regulate voltage, but it's actually sourcing current. So if we treat this as a negative load, we know that this cannot provide voltage support. So the voltage support still has to come from the regulator, still regulating the circuit, and we still have load and therefore drop across the circuit. And so even with the DG online and backfeeding, we still want this regulator to be able to raise the voltage here to support it downstream. And therefore, we would want to select DG mode, and in the reverse power, select a negative R where we had a positive R in forward power mode. Now, our next option up here would be something referred to as regulate in reverse. And in regulate in reverse, this is reverse power due to switching or sectionalizing. So you can see here we have two substations. Again, they each have a feeder, they each have a downline regulator. This regulator is normally regulating this portion of circuit because we have a normal open tie point. So this is the load side of the regulator, and it's regulating this portion of circuit with that impedance, that load. If we're using RX, it would be calculated off of that. Also notice for time delay, we're coordinating. So if the LTC is set at 60 seconds, this regulator would be set at 75. Same here, LTC set at 60, first set of downline regulators would be set at 75. This regulator's load side is right here, so the PT is right here to monitor the load side voltage. And if we're using line drop, we're regulating this portion of the circuit, so we would be calculating our R and our X off of that impedance and that load flow. So that's in the normal mode. But now if we have a fault, so this is again our normal mode, open switch, you can see this regulator is regulating this zone with the power flow going in this direction. This regulator is regulating this zone with it going in this. And then the LTC is regulating up to the regulators if we have it coordinated correctly. And in actuality, it's actually going all the way down to here, because if the time delay is, if the whole voltage is low, it's going to correct everything. So now we're going to open up this breaker. They say we had a fault right here close to the bus. We open up this breaker, or maybe we've just got this breaker out of service. So we're going to close in our normal tie to pick up this load onto this substation now. So now you can see we have changed our zones that each regulator is regulating. This regulator, which was regulating only up to this point, has additional load that it has picked up. This regulator, which was regulating this circuit prior, is now actually regulating this piece right here. So, what are the issues that we can have? Well, let's start with time delay and coordination again. If we want to coordinate properly, this is still set at 60, this is still set at 75, but now this is actually coordinating back this way, so it should go to 90 seconds. In the forward mode, it was coordinating back here, so 60, it was set to 75. But now, in the reverse direction, it is actually coordinating back through another regulator and then an LTC. So we need its time delay really to go to 90 seconds. So in the forward direction, we would want the time delay on that regulator to be 75. And in the reverse direction, we would want it to be 90. Our next issue is the line drop compensation. This regulator was regulating this piece of circuit, which had a certain impedance and a certain load characteristic. Now it's regulating this piece of circuit, which is going to have a different load. So it was regulating load area number 2. Now it's doing load area number 1. And therefore, if we are using R and X, we probably need to have different values in the reverse versus the forward to compensate for the fact that we're actually regulating different pieces of the circuit. But finally, the biggest problem is where the PT is. So if we only have one PT on the regulator, we need that PT to be on the load side because that's the only side that the voltage changes on. So in the normal power flow, this is the load side and this is where the PT would be hung. But now in reverse power, this becomes the source side and this becomes the load side. So now I have my measuring PT on the source side. And if I do not correct for that, what will happen is as this voltage gets out of band, the regulator will tap to correct it, but it's only changing this voltage. So because it's measuring this voltage, but correcting this voltage, it'll never see the correction, and therefore you'll have a runaway condition. So we need somehow to get this regulator to look at the voltage on this side of the regulator, which would now be the load side. There are two methods for doing this. Number one is we could hang a PT on both sides and then just switch which PT we're measuring. But assuming first here we only have one PT, the only other thing we can do is we can look at the tap position. And we can calculate, if we know the voltage on this side of the regulator and we know what the voltage is on the other side, we can calculate. So, problems to be solved in Regulate in reverse. First of all, the PT is now on the source side of the regulator, and we really need it to be in the load side of the regulator. And if we do not, we will have a runaway. Secondly, we are regulating a different portion of the circuit, therefore different loading, different impedances, and that will require a different line drop setting, RX settings. And finally, we have the coordination of the time delays. We are coordinating with a different set of devices, and therefore we would need a different time delay. So, with that in mind, what we need to do is when we see reverse power due to the sectionalizing, we first of all need to have a different set of settings in reverse than forward that allow us to have a different time delay as far as a different R and X. And that'll solve the coordination and the line drop problems. Secondly, we need to get the voltage measured on the load side. Our PT is now on the source side. We have no PT on the load side. But again, if we know the tap position on one side and we know the voltage there, we can from that calculate what the voltage should be on the other side of the regulator and use that to compare to the band. But to do that, we have to have correct tap position first of all. So the control has to know the tap position and it has to be correct. And we also need to know what type of regulator, whether it's a type A or a type B. And then once we have this and we know this, we can calculate the voltage and see if we're in band or out of band. Also, we have to reverse our raise and lower outputs in the opposite direction. So, if we had two PTs, we wouldn't need to calculate the voltage. We could actually just switch. And we can say in forward direction, we're going to measure our load side PT. And in reverse direction, we'll measure what was the source side and now the load side PT. And then we would still need to have our different settings for R and X, but we would no longer have to use the tap position. We would not need to know whether it was a type A or type B regulator, and we would not have an issue if the tap position was incorrect. So, that is our other selection up here, is Regulate in reverse measured. And notice it still allows us to select our different R, different X, and different time delays. The only difference between Regulate in reverse and Regulate in reverse measured is measured says there will be a second PT, and one of the advantages of the 6200 over the 2001C and prior platform is they only had one PT input, where the 6200A has two PT inputs. So we can actually wire in a source side PT, a load side PT. The 6200A will only look at one PT at any given time, and there's a relay that switches which of the two PTs actually go into the sense voltage of the control. So in the forward power mode, it would send the load PT in, and in reverse power mode, it would send in the source PT. Other than that, everything else will be the same. So again, the question in reverse power is the source side PT going to be still the source side, or is it going to be the load side? In the case of sectionalizing, it will switch. Now, the reason we need to know the type regulator is because the percentage of regulation is a little different. And if we're going to calculate off a tap position, we got to know how much regulation per tap. So first of all, what is a type A versus a type B regulator? Basically, it's construction internal to the regulator. You still have a source, you still have a load. The difference is, where is the series winding? The series and the shunt windings of the regulator. You can see that the shunt winding on a Type A, or a straight regulator by Siemens terminology, is on the source side. A Type B, or an inverted regulator by Siemens, would be on the load side. So if we can determine where the shunt winding is off the nameplate, we will know whether it's a Type A or a Type B. And typically on the nameplate somewhere, it'll actually say Type A or straight or Type B or inverted. But if it doesn't, all we need to do is we need to look for the shunt winding. If it's on the source side, it's an A. If it's on the load side, it's a B. And why that matters is, if we do the math, we can see for a straight regulator or a Type A, no matter the vendor, what happens is, in the raised position, we have our voltage, our source voltage coming in. If we add up from the SL, we're leaving polarity, and then we're coming through the series winding, leaving polarity. Since we're leaving on both, these two voltages sum up, and since this is a 10% winding at full 16 raise, that would give us 110% of the incoming voltage would be on the output side. And that is 10% per tap if we do the math down here. Now, on the lower side, it's the exact opposite. We're still coming in, leaving the polarity on this one, but now we're entering the polarity on this one instead of leaving it. So now this is going to subtract from that. We would have 100% minus 10%, and if we do the math the whole way down, that still gives us 10% regulation. So in either direction, we're going to have 10% regulation over 16 taps. Is 5/8% per tap, which equates to 3/4 of a volt secondary. So if it's a Type A regulator, no matter the raise or the lower position, if I know what tap I'm on, let's say I'm on 2 lower, then I know that I need to add 1.5 volts to get the voltage on the other side. So if I know the voltage on one side, I can use 3/4 of a volt per tap on the other, either adding or subtracting, and I can calculate the voltage on the other side. But for a Type B regulator, the series winding comes before the source winding or the shunt winding, and it changes the math a little bit. So in the case of a Cooper, instead of having a 10%, they actually put a 9.1 in there. And the reason they do that is, if you put a 9.1 on, then on the raise side, we're still looking at the polarities, and they're summing, and you'll see that we can still get our full 10% regulation. But on the lower side, if we look, we'll notice that we only get 8 3/4% regulation. So what that means is, on the raise side for a Cooper, we're still going to get 3/4 of a volt per tap. But on the lower side, we're going to get slightly less than 3/4 of a volt per tap. And therefore, if we want to calculate the voltage correctly on the lower side in reverse power mode, we need to take that into account. And with GE and Siemens, they still use the 10%. So what that ends up doing is actually giving you more regulation on the raise side and less regulation per tap on the lower side. So you can see on the raise side we're doing 11%, and on the lower we're doing 9%. So with that in mind, if we're doing our calculations, on the raise side we're going to get slightly more than 3/4 of a volt per tap. On the lower side, slightly less than 3/4 of a volt per tap. So when you select which type of regulator in the software, you're telling the control in reverse power mode, or even in normal mode, it will use this to calculate the source voltage. And so it's going to calculate the source voltage by looking at the load voltage and then determining what tap it's on, and then looking at what type of regulator to figure out how many volts per tap to apply. So if we don't have our type right, we could be slightly off in our voltage. And right here under configuration is where we would select which type of regulator to use, either a type A or a type B. And again, this is only really going to affect the regulation if we select regulate in reverse. If we select regulate in reverse measured, this will not matter because it'll actually be using the actual voltage on the other side to measure. But if we only have the one PT and we have to calculate the voltage, part of the calculation, it needs to know which type of regulator it's on. As a final option for reverse power, we have an option called return to neutral. And this is typically being applied when we have a circuit that can receive reverse power either because of a distributed generator or because of sectionalizing. So this control could be seeing reverse power if the switch is open when the generator is online, or it could be receiving reverse power due to the switch being closed and being backfed during sectionalizing. And the control really cannot tell the difference. And it's important to know the difference because, again, if it's due to the DG, then this is still the load side of the regulator. But if it's due to sectionalizing, this is now the source side of the regulator. And so if it's due to DG, we don't want to swap either looking at which voltage we're sensing or calculate the voltage on the other side. But if it's due to the sectionalizing switch, we do. So with the control having no way of doing it, some utilities think the best solution for this would be to punt, basically, have the regulator in reverse power, run to neutral, and then go to a blocking mode until the power direction comes back forward, and then return to regulating. So if you select return to neutral, when reverse power is detected at the regulator control, it is going to run to neutral. It'll run the regulator to neutral, and then it will block until power direction comes back forward again. So, in that mode, we can, again, see reverse power due to two different reasons. Sectionalizing, in which case the PT is on the wrong side. We also need to switch the R and the X, and we also need a different time delay. Or it could be DG, in which case the PT is on the right side of the regulator. We still may need a different R and X, but we do not need a different time delay. And because we have to do it differently depending on which of the two, and we cannot tell, we just kind of determine and leave it alone. Now, in our next version of firmware, we will be releasing a smart version of this. And what we'll be doing is, in reverse power mode, you select one or the other, even if it could be caused by both. And what will happen is, after taking a tap, if we do not see a voltage change after 2 consecutive taps, we'll assume that we're seeing reverse power for the opposite reason and then switch. So for instance, if we saw reverse power due to DG, but we actually had it set to regulate in reverse, when we set regulate in reverse, we're switching the PT to the source. The source is still the source, so it's not going to change. After 2 taps, we'll say, hey, we're really not in reverse power due to sectionalizing, and we will automatically go to DG mode. So that'll be a new feature in the next version of firmware that we'll be calling Smart Reverse Power. And in that mode, you really would not need to have the return to neutral, but it'll still be available if you want to. So in summary of reverse power's definition is defined by the power bias mode. So first of all, reverse power is always only looking at the real portion of the current, and depending on the setting of the reverse of the power bias mode, we may need 4 milliamps for 5 continuous seconds to bring us into either direction from the other, Or we may have the 4 milliamps only go one direction, and then anything the other direction may bring us out. Once we know which direction we're in, we have different modes we can apply. Block is, if I see reverse power, I don't regulate until I come back into forward mode. Ignore says, if I see reverse power, I basically don't care. I'm going to use my forward settings and regulate exactly the same in forward as I would reverse. Regulate in reverse says that my source is now my load and my load side is now my source side. So I need to go to reverse settings, and I also need to measure the other side of the regulator. And if I don't have a PT, then regulate in reverse says use the tap position. You're on the source side, measure the voltage on the source side, use the tap position to calculate what the voltage should be on the load side, and then that's the voltage you compare to band. Where regulate in reverse measured says I have PTs on both sides, so instead of having to calculate off the tap position, I'll just switch which of the two PTs I'm looking at. DG mode is made for distributed generation, and that says that if I see reverse power, it's probably due to a DG, and I need to flip my RX, because if I don't, I can under voltage customers at the end of the circuit. Because if I'm using a positive number of R to boost the voltage in the forward direction, that will actually cause the regulator to reduce the voltage in the reverse direction. The current sign is being changed from plus to minus, therefore the voltage will be from plus to minus. So in order to correct that, we need to put a negative on the R. So we would have a positive R in the forward direction, negative R in the reverse direction. And return to neutral is for those circuits where you can have reverse power due to either DG or sectionalizing. The control doesn't know which is causing it. It knows that it has to treat it differently. Therefore, the safest way of approaching this would be to run the regulator to neutral, lock it down, block it until power direction comes back forward, and then return it back to service. But in our next release, we will be adding a smart mode that will allow you, in the case where it can see reverse power due to either, allow you to pick which one you think is the most likely, and we'll start with that assumption, and if we're correct after we tap, we'll still see the effect. Because with DG, the load side is still the load side. With sectionalizing, it's not. So if I do a tap and I still see the voltage change after that tap, I know I guessed right. If I go 2 taps and the voltage is not changed, I know I guessed wrong, and I can then automatically switch to the other mode. So hopefully this has been a beneficial summary of how Beckwith Electric's M-6200A treats reverse power, going through some of the settings, and we are going to have a couple more slides coming up. If you're interested in the DNP portion, we'll be showing you the different DNP points available for reverse power. So in finishing up our reverse power presentation, we're going to look at a couple DNP points that are helpful to remotely know what's going on. First of all, we're going to be looking at our binary input points, and there are 2 binary inputs that are key. One would be power flow direction. That'll be a 1 when we're in forward and a 0 when we're in reverse. That'll tell you dynamically real time what mode or what direction the control thinks it's in. And second would be the reverse power block in effect. That point will be a 1 when the control is blocking due to reverse power, and a 0 when it is not blocking. So those would be the 2 binary inputs that we would recommend that we monitor, especially if we're going to be blocking on reverse power. Now, there are a couple analog points we can monitor that aren't shown. These are analog outputs. But on the analog inputs, the only 2 I would pay attention to are tap position and megawatts. Now, the definition of Beckwith Electric for megawatts is positive megawatts flowing out of the load side of the regulator. So if we see positive megawatts, that's an indication we are in forward power, and negative megawatts would be an indication that we are in reverse power. We would also want to pay attention to the tap position, because if we're going to select regulate in reverse, we're going to be using the tap position to help determine how to regulate the voltage. And if the tap position were to get off, obviously the voltage will not be regulating correctly. So those would be the two analog inputs. On the analog output side, you can see that we have reverse bandwidth, band center, time delay, R and X's that we can set remotely or change the setting of. And then the last setting would be the reverse power operation. That is the setting that allows you to change it from block to ignore to DG to regulate and reverse and so on. So those would be the typical values that we may want to be bringing back to SCADA, monitoring, and possibly changing remotely when we're looking at reverse power. So hopefully this has been beneficial. We thank you for taking the time to review this material. We always welcome any comments, questions, concerns. All that can be submitted via the same portal that you're currently viewing this on. And we hope to see you with another session. Thank you and have a blessed day. Bye-bye.